Polyvagal Theory, A Science of Safety. It's written by Stephen Porges, printed in Frontiers in Integrative Neuroscience, open access, published May 10th, 2022. Contemporary strategies for health and well-being fail our biological needs by not acknowledging that feelings of safety emerge from internal physiological states regulated by the autonomic nervous system. The study of feelings of safety has been an elusive construct that has historically been dependent upon subjectivity. Acknowledging that feelings of safety have a measurable underlying neurophysiological substrate would shift investigations of feelings of safety from a subjective to an objective science. Polyvagal theory provides an innovative scientific perspective to study feelings of safety that incorporates an understanding of neuroanatomy and neurophysiology. This perspective identifies neural circuits that down-regulate neural regulation of threat reactions and functionally neutralize defensive strategies via neural circuits, communicating cues of safety that enable feelings of safety to support interpersonal accessibility and homeostatic functions. Basically, when humans feel safe, their nervous systems support the homeostatic functions of health, growth, and restoration, while they simultaneously become accessible to others without feeling or expressing threat and vulnerability. Feelings of safety reflect a core fundamental process that has enabled humans to survive through the opportunistic features of trusting social engagements that have co-regulatory capacities to mitigate metabolically costly defense reactions. Through the study of neurodevelopment and phylogeny, we can extract foundational principles and their underlying mechanisms through which the autonomic nervous system leads to feelings of safety and opportunities to co-regulate. Several principles highlight the validity of the science of safety that, when implemented in social institutions, ranging from healthcare to education, would enhance health, sociality, and lead to greater productivity, creativity, and a sense of well-being. By respecting our need to feel safe as a biological imperative linked to survival, we respect our phylogenetic heritage and elevate sociality into a neuromodulator that functionally provides the scientific validation for a societal focus on promoting opportunities to experience feelings of safety and co-regulation. Introduction. Contemporary strategies for health and well-being fail our biological needs by not acknowledging that feelings of safety emerge from inside the body. This paper focuses on feelings of safety, an elusive construct that has historically been dependent upon subjectivity. It's proposed that feelings of safety have a measurable underlying neurophysiological substrate. Acknowledging that feelings of safety are an emergent property of autonomic state would shift investigations of feelings of safety from a subjective to an objective science. In writing this paper, I've reflected on a personal question: what principles can be extracted from conducting empirical research for more than 5 decades? What principle has captivated my passion and intellectual curiosity? What theme would I use to organize the information from my papers, books, or talks? Or simply phrased, what have I learned? After reflecting on this question, I arrived at a concise, intuitive principle that humans, as social animals, are on an enduring, lifelong quest to feel safe. This quest appears to be embedded in our DNA and serves as a profound motivator throughout our life. The need to feel safe is functionally our body speaking through our autonomic nervous system, influencing our mental and physical health, social relationships, cognitive processes, behavioral repertoire, and serving as a neurophysiological substrate upon which societal institutions dependent on cooperation and trust function are based. Feeling safe functions as a subjective index of a neural platform that supports both sociality and the homeostatic processes, optimizing health, growth, and restoration. Operationally, feeling safe is our subjective interpretation of internal bodily feelings that are being conveyed via bidirectional neural pathways between our bodily organs and our brain. Feelings of safety are not equivalent to an objective measurement of safety, which may pragmatically be defined as the removal of threat. Feeling safe is more akin to a felt sense, as described by Genlin. Although Genlin as a philosopher and psychologist was not physiologically oriented, he described a felt sense not as a mental experience, but as a physical one. In understanding the motivation to feel safe, feelings of safety may be conceptualized from the polyvagal theory. Polyvagal theory provides an innovative scientific perspective that incorporates an understanding of phylogenetic shifts in vertebrate neuroanatomy and neurophysiology. This perspective identifies neural circuits that downregulate neuroregulation of threat reactions and functionally neutralize defensive strategies via neural circuits communicating cues of safety. Feelings of safety are operationally the product of cues of safety via neuroception, downregulating the autonomic states that support threat reactions and upregulating autonomic states that support interpersonal accessibility and homeostatic functions. Basically, when humans feel safe, their nervous system supports the homeostatic functions of health, growth, and restoration, while they simultaneously become accessible to others without feelings or expressing threat and vulnerability. In explaining the profound importance of feeling safe, we are immersed in the ambiguity of our language when it comes to describing feelings and linking feelings to underlying neurophysiological states. This problem dates to the earliest psychologists, such as Wundt, who adopted and standardized introspection techniques to explore sensations, which we essentially limited to external stimuli. Polyvagal theory leads towards a hierarchical conceptualization of feelings as higher brain interpretations of the neural signals conveying information regarding visceral organs, such as the heart and gut, to the brainstem. This psychophysiological perspective emphasizes the foundational function of autonomic state in the subjective experiences of global feelings and specific emotions. Within this hierarchical conceptualization, the feelings of safety are preeminent and form the core of an enduring motivational system that shifts autonomic state, which in turn drives behaviors, emotions, and thoughts. The resulting model suggests that feelings of safety reflect the foundational autonomic state supporting maturation, health, and sociality. In an earlier paper, Porges 1996, a hierarchical model of self-regulation was proposed to provide insights into optimizing intervention strategies for high-risk infants. The model reflects maturational competencies in neuroregulation that provide a substrate for the more complex co-regulatory social behaviors. The main point of the model is that higher behavioral functions, which are frequently intentional, are dependent on the functioning of the more survival-focused foundational systems embedded in the brainstem. The levels are described in Table 1. Level 1 is focused on the function of brainstem structures in optimizing physiological homeostasis through neural and neurochemical bidirectional communication between visceral organs and brainstem structures, which regulate the autonomic nervous system. The neural pathways involved in Level 1 are functional at birth in healthy full-term infants. An index of Level 1 can be derived from quantifying respiratory sinus arrhythmia, a periodic component of beat-to-beat heart rate variability that is synchronous with spontaneous breathing, and a valid index of cardiac vagal tone via ventral vagal pathways. However, in the preterm infant, the system is not sufficiently mature, and the amplitude of respiratory sinus arrhythmia is notably low. Provides a more detailed description of the maturational changes in the neuroregulation of the autonomic nervous system as a neural platform for social behavior. Level 2 emphasizes connections between higher brain structures and the brainstem. In regulating autonomic state, success in Level 2 is achieved when the suck-breathe-vocalize circuit is integrated with the ventral vagal pathway. This circuit enables nursing and soothing to occur and is dependent on the neural pathways that define the ventral vagal complex. As higher brain structures via the cortical pathways regulate these brainstem nuclei of the ventral vagal complex, the pathways are subsequently repurposed as an integrated social engagement system which foster social communication and co-regulation. It is through these connections that safety cues can recruit metabolically efficient states of calmness, example slow heart rate, to optimize health, growth, and restoration. Or, alternatively, threat cues can downregulate the social engagement system to optimize metabolically costly strategies. The metabolic requirements for fight-flight behaviors require resources to be diverted from homeostatic functions. Autonomically, this is observed through the disengagement of the vagal brake. In safe social settings, the vagal brake is dynamically adjusting heart rate to match the metabolic needs of the behavior. The ability to disengage the vagal brake when motor behaviors, which are required in social interactions, are related to subsequent competencies in social behavior. More recently, a new metric, vagal efficiency, was introduced to describe the dynamic efficiency of the vagal brake. Example, the cardio-inhibitory pathways to the heart monitored by quantifying the amplitude of respiratory sinus arrhythmia in regulating heart rate. This metric evaluates the slope of the regression line between short time periods of synchronous measures of heart rate and respiratory sinus arrhythmia. Functionally, the slope is providing an estimate of how much heart rate would change with a standardized unit change in the amplitude of respiratory sinus arrhythmia. This metric has been useful in evaluating sleep state in full-term newborns and the maturational trajectory in preterm infants. It's also sensitive to alcohol and may serve as a potential indicator of dysautonomia, since it's greatly depressed in individuals with an adversity history and in those diagnosed with hypermotility subtype of Ehlers-Danlos syndrome. In the context of this chapter, Level 2 provides the foundational neural platform for feelings of safety and access to the circuits that would enable a neuroception of safety. Table 1 emphasizes the hierarchical nature of specific autonomic states and accessibility of behaviors that we cluster as self-regulation skills. The optimal function of each level is contingent on each of the preceding levels being adequately functioning. Observers of developing children are aware of the strong maturational influence that pushes the child through the sequence. However, few are aware of the parallels between the development and evolution of how this information informs us regarding the adaptive functions of specific autonomic states. It's not that a specific autonomic state is good or bad, but rather what adaptive functions did ancestral vertebrates access while being in a specific autonomic state.